so hi everyone. Thank you for being here today for what promises to be a very interesting talk by Professor Sébastien Francoeur. And so it will be on the characterization of materials by spectroscopic methods. And in particular, we will get to hear about his group's latest investigations into phonon polaritons in van der Waals materials, and this through the lens of Raman spectroscopy. Sébastien completed his Bachelor of Engineering at Polytechnique, then his master's from Texas Tech University, and obtained his PhD from the University of Colorado Boulder. He then went on to complete a postdoc at the National Renewable Energy Laboratory before joining Polytechnique, where he has been since 2005. Thank you so much for being here, Sébastien. The floor is yours.
All right. Merci, Nicolas. Good morning, everyone. It's a pleasure to be here with you this morning and talk about our recent work on phonon polaritons. All right, here is my conclusion slide. Okay, I'll present this at the end of the presentation. What I would like to just convey in this first slide is the main points of this presentation. Now, phonon polaritons have been extensively studied in the last 10 to 15 years. But if you were to do a survey of the investigation that have been published, you would find out that 90 to 95% of all these papers were using a single instrument for these investigation. This instrument is called SNOM for scattering type, scanning near field optical microscope. It's a tremendous technique that imaged the propagation of phonon polaritons. However, this is not the most accessible technique. It combines an AFM and it combines a whole spectroscopy system together. And as such, only a few dozen research groups around the world are mastering this kind of experiment. In this presentation, I'll present results on phonon polaritons that use Raman spectroscopy in a backscattering configuration. And using this technique, we can get the same information, dispersion curves, confinement factors, group velocities, and so on, as you can get from SNOM. And I'll describe what are the advantages and disadvantages of this technique with respect to the other one. But one of its main advantages is that it is a very common technique. It is available virtually in all labs working on 2D materials around the world. So in contrast to SNOM, this is easily accessible. And also, if you were to survey the same literature and look at what hyperbolic materials were studied, you would find out, again, that 90% of the literature concerned only two materials, boron nitride and molybdenum trioxide. These are very good materials, there's no doubt about it. But the range of hyperbolic materials in 2D materials is exceedingly large. It's a bit surprising that only two materials were studied or extensively studied so far. I'll introduce a new material, gallium selenide, that has figures of merits that are matching or surpassing these two polaritonic materials. So in these two demonstrations, the democratization of the instrumentation and the introduction of a new material, I hope that these contributions may help accelerate the development of polaritonic applications. All right, that was the two key points. Let's step back a little bit and talk about polaritons. You must have heard about these things, right? Because they've been extensively studied in the last decade or so. Now, whenever you have a solid, you can have a very large number of excitations in these solids. Many of these excitations will be polar in nature. Let's take, for instance, an exciton, which is an electron and a hole forming together this exciton. Naturally, this is a dipole. This dipole can oscillate and it can propagate in the material. As it propagates, you'll have the dipole that generates an electromagnetic field. This electromagnetic field must obey Maxwell's equation. And therefore, you'll have a significant coupling between this material excitation, which is the exciton, and light. And when the two are strongly coupled in certain regimes of frequency, we'll call this a polariton. Exciton polaritons have been extensively studied in the last decades or so. These are excitation that you can find mostly in the visible range of the spectrum. You have plasmon polaritons in the near infrared. You can have magnon polaritons. It's a magnetic counterpart in the microwave. And what I will talk about today are phonon polaritons. Phonons are crystal vibrations or atomic vibrations in the crystal. Some of these phonons will be polar in nature, and as they propagate, they will be coupled with light as well. So in this presentation, whenever I say polariton, I mean phonon polaritons. Let's go a little bit more in detail about the interaction between these two excitations in a solid. So here I have the dispersion curve of two types of excitation. So here I have frequency, wave vector, and the wave vector is rather small, much smaller than the size of the Brillouin, so that we can see the dispersion of light inside the material represented by this dotted line. Polar phonons will also have some form of dispersion, but on this scale, the polar phonons will have two states, a longitudinal optical phonon and a transverse optical phonon at slightly different energies. The transverse phonon will interact with the transverse light, and therefore, instead of crossing here, if they interact strongly, they'll create two new states, the lower polariton and the upper polariton band. Whenever you see the polariton touching either the phonon line or the light line, that means the polariton has lost mixed character. So here, it's pretty much behaving like light. Here, it's pretty much behaving like a phonon. It is in this region, close to the crossing, that the interaction is maximum, and where you have a superposition state of a solid state excitation, the phonon, and light to make a polariton. What's quite interesting is that this superposition state in this region will have characteristics which are quite different from that of light or the phonon. And that gives you a lot of room to play with the characteristics of polaritons, and that's why they've been so successful in recent years. Okay, but let's talk about the propagation of polariton inside first the most simple material, a bulk isotropic material. And to analyze the propagation, we need to first look at the permittivity in the vicinity of these phonons inside the material. These phonons are characterized by these two frequencies, TO and LO. Now, below TO, the permittivity is positive, and as we go close to the TO frequency, it sharply increases. It becomes negative in between these two frequencies. This is what we call the restreint band. In this region, the polarization of the material is opposite to the incident field, screening the field, and therefore the material will be highly reflective. And above the LO frequency, the permittivity becomes positive again. If we look at the polariton propagation curve or dispersion curve inside the material, it is given by this very simple equation. We have permittivity that must be equal to this quantity where we have the propagation wave vector and the frequency. So if you select a given frequency inside an isotropic material, you'll have this kind of iso frequency propagation curve. That is, for a given value of this is a constant, this is positive, what you get is a sphere. So your polariton can propagate in any directions. So the wave vector will be at the surface of this sphere for a positive value. Okay, so polaritons can propagate in any direction. Now, when we add a negative permittivity, what's quite interesting is that the propagation wave vector will become imaginary. No propagation can exist in the bulk material in this region. However, there also can be states at the surface of the material. So when you bring in an interface between this material and, let's say, vacuum, you can have a solution which will be a decaying exponential or an evanescent wave in both air and in the material. And that's what you get as a dispersion. So in a bulk isotropic material, you can have lower polaritons, upper polaritons, and surface polaritons that will propagate. Now, to make things a bit more interesting, let's confine them. So instead of having a bulk material, we'll just decrease the thickness of the material, at least in one dimension. So we have a slab, and we have a propagation wave vector, okay, so that the polariton propagates like this. But the perpendicular wave vector like this, because of the finite thickness, will be quantized. Now, for non-polaritons to propagate in the material must be confined. So here at the top interface and bottom interface, what we'll have are decaying exponential and propagation here in the layer. So if we look at guided polaritons, we'll have decaying exponential on the outside, and then we have the fundamental mode, the first excited and the second one, and so on. If we plot the isofrequency curves, we at a given frequency, we'll find out that in this isotropic material, the polariton can propagate in the plane of the sample following these circles, right? The wave vector must be on one of these circles, depending on which mode you get. Now, surface polaritons, they have decaying exponential at both the top and bottom interface. And if the layer is thin enough, these two modes will talk to each other and form what we call the symmetric and antisymmetric mode. They will propagate also isotropically inside the sample. If we combine all of this on a dispersion curve of omega versus k, we have in this region of positive permittivity several guided modes that can exist because of the confinement. In this region of positive permittivity, same thing. That will be the upper guided confined polaritons. And under the stratum, you'll have the symmetric antisymmetric mode and their dispersion. Okay, now let's make things even more interesting. We're going to look at what's happening in an isotropic material. And in recent years, isotropic materials have been all the rage because every time you take a 2D material that can be exfoliated, necessarily this material will have strong anisotropic characteristics. And this is the case for gallium selenide, a bit of the star of this presentation, which is just a 2D material. Here's a monolayer, here's a second one that can be easily exfoliated. If we look at the permittivity of this material in the range where we find some polar phonons in this material, we'll find that we have two permittivities. The one which is aligned along the out of plane direction, epsilon parallel, and the one perpendicular to it, or in plane. We're finding out in this energy lower than the TO that will have positive permittivities. They're different, but positive, leading to an isofrequency surface, which will be an ellipsoid. If we go right here, we have positive permittivities, but now the sign, the magnitude are reversed. We'll have an ellipsoid as well, but in the other direction. This is not so interesting. What's most interesting in these regions where at least one of the two permittivity is negative and the other one is positive. What happens if you take this formula representing the propagation of polaritons and put a minus sign? Well, you will transform this closed surface into a hyperbolic surface that will be open. And this is the interest of hyperbolic materials. So here we have a type, what we call a type 2 hyperbolic material in this region and in this region. But in this region here, we have both permittivities, which are negative. So I call this a double estragon. Okay, now I want to emphasize the interest for this hyperbolic dispersion relationship, because that's very important for understanding all the interests of the phonon polaritons and many other types of polaritons as well. So I presented this simple equation, and when both permittivities are positive, we get the propagation curve like this in k-space for a given frequency. Now, the first thing we will find out is that the maximum value of k is either here or there, and it will always be bounded by the frequency we have put in this equation. If I want to increase k, I need to select a new frequency that will be higher so that I can have a larger ellipsoid. So k values are always bounded by the frequency at which we're working with. If you look at the propagation, if you can launch in this material a photon polariton that has a wave vector like this, but a little bit of strand in the wave vector, they will propagate with different angle. Yes.
I just have a very, very basic question. So if I have a 3D material, there are normally two transverse modes. So in this case, is only one of the transverse modes active, or are they degenerate?
They're degenerate.
Okay.
So if we have, okay, it depends on what material we want to be in. In this nomenclature here, I have two, I'm showing only two of them. So this would be my uni-ax. This will be the degenerate one.
Yeah.
So we could take this and make a revolution, okay, over the axis to get the other direction.
Okay.
So I have dispersive propagation because for a given value, if I have a slightly uncertainty on k, they will all propagate here with different direction. And the group velocity will be relatively high, so nothing interesting there. Now, when we have one of the two permittivity, which is of a different sign, things get interesting. The dispersion now will be open. This is what we call an hyperbolic dispersion curve. Now, as you can see, k values are not bounded by frequency, because for a given frequency that could be very low, I can always go on this line further and further with higher k vectors. And what is k? K is 2 pi over lambda. If k gets extremely high, that means the wavelength of this excitation in the material gets smaller and smaller. That means I'm concentrating the energy or this photon polariton in a smaller and smaller volume. So that leads to extreme localization of the energy and the information that the polariton carries. Now, whenever I am on one of these long branches, the group velocity is always perpendicular, shown by these arrows. So there's no more angular dispersion here for the propagation, even if we have some uncertainty in the k vector platform. So we have directional propagation. If you look at this curve here, you will see that for a zero change in frequency, you could have a large change in the wave vector. This is the group velocity. So the propagation speed of the light, the group velocity, will get very small. And naturally, for a given frequency, we can have a very large number of states. So the density of state would be large. Yeah.
What limits this? How far can you go over a curve?
Yeah, that's a good question. Naturally, I would say that you eventually will be bound by lifetimes of these excitations and so on, and maybe material perfections and other aspects. But naturally, we're not expected to go to infinity. There's going to be some limits, and the highest confinement factors. So this is the confinement factor is calculated using k in free space and the k that is achieved in the material. So if the wavelength in the material gets much smaller, the confinement factor can be as high as about 100. Okay, so that's the maximum that can be achieved.
What wavelengths does that correspond to?
Okay, so in gallium selenide, the wavelength in vacuum we're talking about is 40 micron. If you go in HBM, it's going to be, I think, if I remember well, about 15 micron. So basically, photon polaritons, they have huge wavelength. And whenever you put them inside the material, you can strongly confine them, okay? Play with this dispersion curve and achieve Ks that will be significantly smaller.
Micron.
So for example, submicron. So what we have achieved is about 400 nanometers, a factor of 100. Okay, so basically, this is why these hyperbolic dispersion curve and hyperbolic materials are quite interesting. And this is a figure taken from a review paper on polaritons published several years ago, where basically polaritons are motivated. But for the special case of hyperbolic polaritons, many applications can be imagined. For example, by concentrating infrared light, we can imagine making integrated infrared circuits that are much, much smaller. By controlling here the concentration of light, sub-diffractional focusing or imaging has been achieved. Because we concentrate the energy as well, we can have extreme nonlinear effects that can occur in this material. And again, by increasing the density of state, concentration of intensities, we can achieve regime of very strong light-matter interaction. As you may well know, all processes of emission and absorption are often, governed by the electrical dipole moment, right? Because this is the dominant term in the expansion of light-matter interaction. We can do this approximation, or this term is dominant, because usually the object that emits light is much, much smaller than the wavelength it exists. If we can confine or reduce the wavelength of the emitted light to a smaller and smaller volume, close to the size of the emitter, we can achieve new regimes of light-matter interactions that would make, for example, 2-photon emission more probable, or at least as probable as single photon emission. And this is very interesting for all kinds of applications. All right. Now, let me just say a few words on how these can be investigated. And I've already mentioned that basically phonon polaritons are confined. That means they have evanescent wave at the surface of the phonon polaritons. So we cannot couple far field light source and a far field detector to these phonon polaritons. So we need to apply some tricks to do a wave vector matching. So two, early techniques that were used, but not so much anymore, are placing a prism on the polaritonic material. And by launching like this way and using total internal reflection, as you may well know, generates an evanescent field, okay, that will excite and launch a phonon polariton in the material. You can use a grating. So you pattern the surface of your sample with a periodicity which is close to the wave number you want to launch, and that can be used to convert far field to a near field that will excite and launch a phonon polariton. But the most successful technique, as I've mentioned, is scattering snub. And this is a beautiful technique. So you just take an AFM metallized tip, bring it to the sample of interest. Now, here you have a near field, interaction. And if you take light from the far field, like a laser, for example, shine it on the tip, the polarization that will occur at the tip and the surface of the sample will do this wave vector conversion required to launch a polariton in the material. Then this polariton can travel. It will travel and then be reflected at the edge, come back, and then it will be outcoupled in the far field and detected. So if you use this technique and you scan the tip at the surface of the sample and you measure the intensity of the outcoupled light, what you will be imaging are the standing waves created by the phonon polaritons in the material. So for example, this is taken at a single frequency of illumination. And what you can find is close to the edge, a maximum, minimum, maximum. And that allows you to easily calculate what is the wavelength of this standing wave. And because you have set the frequency, you can place a point here on this graph of the frequency versus the inverse of wavelength or the wave vector. This technique has been almost, like I said, the only technique used so far, and it provides striking images, that are very beautiful to watch. Okay, I'm going to switch now to discuss Raman spectroscopy, and I might have suggested from the things I said in the first few slides that the Raman spectroscopy of phonon polaritons is a completely new thing, but in fact, this is not quite true. If we look at the history of polaritons, the very first polaritons that was discovered was a phonon polariton. And it was discovered using Raman spectroscopy, 1965 in 3,5 semiconductor gallium phosphide. But I'll explain why it could be done and why it's not been replicated recently. Okay, so here's we have the frequency, propagation wave vector, we have the light line, and we have the TO polar phonon inside the material. Now let's look at what is the wave number here that corresponds to the crossing of the light line in the phonon. And we find that it's very small, 10 to the minus 3 inverse centimeter. It's very small. In order to be accessing this region, we'll need to launch polaritons that have very small wave vectors. And the way to achieve this, I'll go in a bit more detail in the next slide, is by sending the laser light of the Raman system from this side of the sample. The light refracts in, scatters, refracts out. If you want to have such a small wave number, you have to look at a very tiny angle here, about 1, 2, or 3 degrees. Okay, you need to go in forward scattering. And this is a configuration that's almost never used in Raman spectroscopy. Much more difficult in internet. It's not impossible, but it's not the configuration that people use. But successful for achieving the low wave numbers required to image, for example, here the lower polarity range. Just to emphasize this point a bit more, so we have wave vector conservation from the light the laser light that comes in, the scattered light that goes out, okay, on the other side, and here's the polariton that we have launched. If we bring this angle close to 0 and this outside angle close to 0, we know that we can launch polaritons with wave vectors that can be arbitrarily small. So let's look at again the polariton dispersion curve. So here we have 0, and here we have about 10 to the 4 inverse centimeter, relatively small value. We see that at 2 times 10 to the 4, we're far from the crossing. What we see are just mechanical things. So we need to get there, but in forward, that's pretty easy. We can, by scanning the observation angle, we can select which K, we're probing in the sample. Now, let's look what happens in backscattering. Virtually all Raman systems that I know, except one of them in my lab, is doing backward Raman scattering. They're much simpler to implement and to use and so on. So what we do is we send the laser light on the surface of the sample. It refracts in. This is the scattering point. A polariton is launched, and light, to be detected, must be going back, okay? And therefore, we have the light that goes out at a different angle. But if we look at the wave number of the light that's being used for a wavelength that is indivisible, let's just take 500 nanometer, we'll find that the wave vector of the light is 10 to the power 5 inverse centimeter. This is huge. That means that the lowest polariton wave vector we can launch is 2 times this value. Okay, but you may have heard that when you do Raman spectroscopy, you do the spectroscopy at the center of the Brillouin zone, at the gamma point. That's often what is repeated all the time. But that's confusing. And the reason why people say that is that if you look at the phonon dispersion curve, when you look at these curves, you go from the gamma point to the edge of the Brillouin zone. The edge is at an extremely high value, okay, of wave vectors. So when you do Raman, when you're at 10 to the 5, you are at the 1,000th of this distance. So for our practical purposes, people say that they're looking at phonons at the gamma point, and people imply K equals 0. But it's far from the truth, because if you look at the polariton dispersion curve, 10 to the power 5 is not even on this graph, it's very far. And so you're already in the mechanical regime where all light components of the polariton has disappeared. Okay.
So can I ask a quick question?
Yeah.
I think so. The limit here that you're talking about is due to the momentum transfer. Right?
Yeah.
And so you need that if it's 2Q, then you're saying you have complete backscattering.
So if I'm looking at the light that's scattered back in this direction, that means the length of this wave vector is very long.
Yeah. But if you're just measuring the in-plane momentum transfer, it's much smaller. So is it
okay? Yeah, we'll come back to this. Then
just looking at
okay, when I go, but so a little bit later, when we look at thin layers, we'll be tuning the in-plane momentum. momentum that can be zero.
Yeah.
But the net momentum will always be significantly higher. Okay, so the reason why we'll be able to observe phonon polaritons in the backscattering configuration is simply because momentum selection rules will be relaxed. Okay, so this will not fully apply. I'll talk more about this later. A few experimental details about the experiments we did about the material, the setup, and Raman spectroscopy. So, as I mentioned, we've used a material that's called gallium selenide. It's not the most popular 2D material, but it's a very interesting one. Can be easily exfoliated. The two interesting aspects that are worth mentioning is that it has a direct band gap, about 2 electron volt in the bulk form, and the dipole orientation that corresponds to the lowest band gap in this material is out of plane. So if you have your sheet of gallium selenide, the emission dipole is in this direction. For most other 2D materials, it's in plane. So that's a bit of a peculiarity, but that's quite interesting. And the other aspect is that this material is characterized by a very strong nonlinear coefficient. And we'll see that this bears relevance to the experiment that we did. This work was done in collaboration with Polytechnique and University of Montreal. All the experimental part was done in this building in my lab. Most of the work was done by a PhD student, Alaric, and helped with 2 master students, Clément and Arnaud. Okay, exfoliation is done in a very traditional way. We're not doing anything special. Before we study the samples using Raman, we do some visual imaging, AFM for the thickness. And all the experiments we like to do in a vacuum cell. We don't encapsulate the sample because we want to measure pure phonon polaritons unaffected by too much by the environment. But doing Raman spectroscopy for several hours on a very thin sample can be challenging for that poor sample. So we like to do it in an inert environment to keep it, preserve its quality. Okay, I won't go into this slide in great details. I just want to hand-wavingly describe what is Raman spectroscopy is for those that do not know too much about it. So whenever you send an electromagnetic field, that's our laser light, onto the sample, you will create a polarization inside this material. This polarization will be proportional to the product of the polarizability of the material times the incident electric field. Now, the polarizability of the material can be thought as something static, but in fact, all the excitations that can exist in the solid state will modulate at particular frequency this polarizability. So when you have the product of 2 quantities that oscillates in time, you will then generate new frequencies. So the polarization of the material will be at different frequencies, close to that of the laser, but separated by frequencies related to these materials' excitation. So Raman spectroscopy will allow us to measure the frequency of the phonon polaritons that are modulating the polarizability. What's quite interesting, and I've just briefly mentioned from this quantum development, is that Raman spectroscopy, when you look at what is happening in the energetic level structure of the material, can be summarized with a few selection rules, 4 of them. Selection rules on the optical transitions, vibrational transitions, and electron-hole interactions. And these selection rules is basically what conveys so much power to Raman spectroscopy, because we can go deep down inside the physics of what's occurring in the material and extract very powerful information. The experimental system is very straightforward. So we have a sample that's placed like this. We send laser light like this, okay? Very narrow in frequency. And then basically we look at the light that's scattered back, send it to a spectrometer, and analyze the frequency. We subtract the frequency of what's observed with that of the laser, and that gives us the frequency of the polaritons we're looking at. Now, the only thing that's a bit special about this system is that we want to launch polaritons that propagate, in different directions in order to reconstruct their dispersion curve. So if your sample is flat like this, you send light like this, it's scattered back like that, you send a polariton that goes this way. and the in-plane wave vector is equal to 0. Now, if you tilt the sample, you have the light that goes like this, comes back like this. That corresponds to a polariton that propagates as a slight in-plane direction. So that will allow us, by tuning this angle with the light, that will allow us to launch polaritons with different wave vectors. Okay, now let's go a bit in the detail of the phonons found in gallium selenide, because a polariton is a combination of light and phonons. Now, we have 8 atoms per unit cell. That means we have in this material 24 vibrational modes. But because we have a van der Waals interaction between these 2 layers, the interaction is very weak, and the 2 Davidoff doublets cannot be resolved, meaning that we only need to consider 12 vibrational modes, which are shown here. Now, not all vibrational modes can form polaritons. Only those that carry an electrical dipole can do so. And those are indicated here by those that have an infrared component, okay? So it means that they have a dipole. We want to study them with Raman, so these phonons must also be allowed in Raman spectroscopy. In this material, we have this one. They're very different in frequencies, and our system works best by looking in this frequency range, so we'll concentrate on this phonon. When we first started working on gallium selenide, we were quite interested by its electronic characteristics and excitonic characteristics. We were not interested in phonons, and at the time we had little clues about phonon polaritons. But by doing preliminary characterization with Raman spectroscopy, we saw phonons that were unaccounted for. So in Raman spectroscopy, you get the intensity of the light that's scattered as a function of frequency, okay, of the excitation in the material. So we have traditional gallium selenide phonons that have been known for a very long time. This one, this one, this one. But in this particular region, which is zoomed here, we saw phonons that didn't correspond to any frequencies that have been reported before. And even if you would think that, oh, it's just a mismatch caused by something, all of the phonons that have these frequencies are forbidden in Raman spectroscopy, so they shouldn't be observed. So definitely, there was something rather interesting. So the next experiment that you can do is measure the same spectrum, but as a function of the angle, tilt angle between the light and the sample. The mechanical phonons, those that are isotropic in this material, whatever the angle from 0 to 45 degrees always stay the same energy. It's true for this one, and another mechanical phonon. But if you look at those new unaccounted phonons, you can see that there's a significant dispersion with angle. And this is a bit unexpected, especially in this frequency range. And now, if we superpose these features with the permittivity of the material, okay, we're finding out that this feature is in the upper castralum of gallium selenide, and this one is in the double castralum. So that suggests that this could be a surface polariton, and this could be a guided polariton. Okay, so this was just on one sample of a given thickness, and we just repeated the same thing and measured dispersion curve. So with this information here, we can convert this angle, and so this frequency is what we measured. This angle can be translated to a propagation wave vector, and by taking all these points, we can reconstruct the dispersion of the phonon polariton. Yeah.
Is the drifting in the lower real? Like it's all
the low, this one?
No, I think that.
This one?
Yeah. The big one next to it.
The big one?
Curving around. Yeah.
Okay. So in this region, we always use the other main phonons, this A1 that's right here, totally symmetric, that shouldn't move. Another one that's right here that shouldn't move as well, as a calibration. Here, there are two difficulties that appear. First, we should expect polaritons in this region. okay? But we couldn't assign with certainty anything going on there. But this polariton, which is a group symmetry E prime, is expected to move with the angle because we have an anisotropic material. And a phonon of this symmetry, depending on the direction it propagates inside the material, the phonon, it's going to exhibit dispersion as well. So we expect dispersion from phonon polaritons, like here, and also a bit about phonons. But I wouldn't pay attention too much about this. And I can say a bit more about the dispersion of phonon, which is wholly incompatible to what we observed for the other curves.
Yeah, that's also, so you said the guided and surface polariton, they happen because you have a smaller sample, right? Or you have a boundary.
Yeah.
So why are the other phonons not affected by that?
Yeah, so that's a good question. The wavelength of the phonon polariton is about 40 micron. So whenever you have, a sample that's thinner than that, you are in a regime where you could achieve some confinement. But naturally, confinement you get only if you have coherence length. Because to form a standing wave, you need coherence over at least the thickness. The coherence length of phonons is very small. Okay, so that's why in order to achieve confinement on the phonons, you need to go orders of magnitude lower thickness. So what I just presented was 650 nanometer thick sample. That's huge. Okay, to get confinement on phonons, you need to go to tens of nanometers. I don't know the exact number, but that's much more difficult. So what it says basically is that what we have is a phonon polariton. The electric field of the phonon polariton help maintaining the coherence of the phonon. Okay, it gives it synchronizes the phonon over distances that are much higher than what is observed for just phonon. Okay, we repeated this dispersion curve for different sample thicknesses, and then we were able to demonstrate that there were significant variations. I won't go over all the information over this graph, it will be too much. And I will show next is simulations of what's going on, okay? So it's going to be a bit easier to understand and see what's going on. But in this lower group of dispersion curve, we were able to identify this as lower surface polaritons, those that are at the interface between our sample of interest and the substrate over which the sample is sitting. We have the upper surface polariton, which is the air sample polariton, and here we have the upper guided polariton. Now, there's one thing I would like to mention here, and that's going to help us mention that basically gallium selenide is a pretty good polaritonic material. I'm going to take this dispersion curve that's obtained at 380 nanometer. If we extrapolate here at this point, we're finding out that we really have a polariton here because the phonon frequencies are very far apart. So we have a strong light component here to generate this frequency. But this occurs at the wave number, which is about 15 times 10 to inverse centimeter. And from this, we can calculate the confinement with respect to the free space wavelength. And what we get is 100. 100 is one of the best confinement values that have been reported so far for phonon polaritons. Using the same curves, we can also calculate the group velocity. And the group velocity we get in our thin samples is about 1% of the speed of light. So there's a significant slowdown. I'll come back to this value a bit later. Okay. Now, this ability to easily probe phonon polariton was making some other researchers skeptic. So we wanted to, demonstrate that indeed we should see these phonon polaritons using Raman spectroscopy. So what we did is calculated polariton Raman spectrum. Okay, I won't go into the detail about the equation that we can use of the model to calculate the intensity of the scattered light by phonon polaritons at a given frequency. But I would just like to say something about the physics because it's important here. Here, you will recognize what we call the Raman tensor that's being contracted by light polarization, incident and scattered. Now, in the case of the polariton, Raman tensor, we'll have two components. The change in polarizability, which is due to the phonon, right? That's modulating the permittivity, polarizability. But also we have a second term. The polariton has an electric field, and this electric field will also modulate the polarizability of the material. And this tensor right here corresponds to the second harmonic tensor of the material. So basically doing Raman spectroscopy on phonon polariton is a kind to a nonlinear interaction between the polariton and the laser light that's being launched. Now there's an integral right here. I'll come back to this integral a little bit later. And what we'll see is that this term represents momentum conservation. In plane, momentum is conserved, perfectly conserved with delta Dirac. But because in the vertical dimension, we have a thin layer, okay? The integral here will be different than zero. That is the oscillation of the polariton field overlapping with the oscillating term involving the change in light momentum will not go towards delta Dirac, meaning that if we had a very thick layer, this would have extrapolated to a delta Dirac, and we would have perfect momentum conservation in all three dimensions. But by thinning down the sample, we're having something that is different than zero. And again, this is a kind of some nonlinear effect that are occurring in materials. Okay, in order to calculate Raman intensity, we need first to calculate the polaritonic electrical field in our sample structure. And the structure we have is air, a sample of gallium selenide, and then which is sitting on an oxide and then silicon. And every bright spot here represents polaritons. Here we have the upper guided polariton, the surface at the air interface, the surface at the oxide interface, and here the lower guided polariton. This is at an angle of 10 degrees, but by varying this angle, naturally, we can add other guided modes and the dispersion can be examined. Now, using this electrical field, we can calculate what is the intensity of the Raman spectrum. And here I would like to note that it's rather unusual to calculate intensities of Raman spectrum and expect to get a good match. And in spectroscopy, matching intensities, especially in optical spectroscopy, is not actually straightforward. But we did attempt it. And here what I'm showing are Raman spectrum at different propagation wave number or different tilt angle. And every vertical line is a spectrum. The dotted lines represent the energy of the different polaritons that we would expect in a sample of this thickness. And we have the lower polariton, which is very weak in intensity. We have the upper guided polaritons, which should be dominant, and the surface polariton, which should be also rather intense. Now, let's compare this calculation, which is shown in the background, okay, and the experimental data point. As you can tell, the dispersion observed experimentally is there, but it's much, much smaller than what we should have expected numerically. And that's bringing us to a limitation of our current Raman setup. Usually when you do a Raman setup, you want to achieve microscopy. You want to measure the scattering using a light spot size, which is diffraction unit. But if you operate at high spatial resolution, that means your K resolution, the K value at which you're sending light is very poorly defined. And in our system that we had configured for microscopy, our uncertainty in the K value corresponding, here represented in a tilt angle, let's say we're centered at 25 degrees. Well, the uncertainty in the angle, or the accident angle of our system was plus minus 5 degrees. So whenever we measure with our spectrometer at a given frequency, well, we integrate the signal over all these wave numbers. Okay? So that's a limitation of the system we used at the time. Naturally, there's different ways to limit this, this problem, but here, this problem, if we work at high angle, is not that huge because the dispersion is rather small. It's when we look at close to zero where the dispersion here is much more important that this angular acceptance is a little bit more problematic. So if we take this calculated spectrum and process it to take into account this finite acceptance angle of our system, what we're finding out is in the background the calculation, and here is our experimental data point. It's not a perfect match, but it matched much, much better. So we could theoretically demonstrate that exactly what we were observing was phonon polaritons. Okay, why can we observe polaritons in Raman backscattering? Let me come back to this integral I've mentioned a bit earlier, the integral of the polariton field over multiplied by this here exponential of the change in light momentum integrated over the thickness of the sample. So on this graph, I'm reporting what is the direction of the scattering as a function of thickness. Now, if we are at very thick layers, okay, 10 micron, 10 micron is very thick. We do have some form of anisotropy, but only a quarter of the light is scattered backward and 3/4 is going forward. But if you decrease the thickness at about 1 micron, half of the light goes forward, half of the light goes backward. So it is because of this integral breakdown of the momentum selection rules in the confinement direction that makes it so easy to measure dispersion, that measures phonon polaritons in backscattering. Now, 1 micron, that's not very thin, right? It's easy to achieve. Whenever you work with 2D materials, some people like to work right here, you know, a sub-nanometer vision. So it's very easy to work at these values. So it's not a limitation. Okay, quickly. So we were able to measure the thickness dependence of these phonon polaritons, and that's a way to engineer the characteristics of these phonon polaritons. We could go from relatively thin, not super thin, but about 50 nanometer to about close to 1 micron. And we see that the evolution of the surface polariton, the guided polariton, matches that of the simulations as well. And the last experimental results. You know that Raman spectroscopy is a technique that's known for its relatively poor scattering cross-section. So you need to send a lot of photons, and you're going to get a few of them back, okay? That's at best. And that's what we did actually. So if you look at, we use the wavelength of 532 nanometer in the green. And whenever the wavelength that we use doesn't match any particular resonances in the material, the scattering intensity will be rather inefficient. But if you can bring this wavelength in resonance with an electronic transition, and in particular with an exciton inside this material, the scattering efficiency can increase by several orders of magnitude, making Raman spectroscopy a much more useful technique, for extracting weak signals. So here are a spectrum obtained with green light, far away from any resonance. We have a mechanical phonon here and 2 upper guided polaritons, which are much smaller, and a surface polariton, which is very small as well. By bringing the light not in resonance, but close to the exciton energy in this material, okay? We're not quite at it, only 40 millectron volt away, what I call quasi-resonance. You can see that the mechanical phonon intensity is rather low compared to the guided polariton, meaning that our signal-to-noise ratio is significantly enhanced. And then, in this particular regime, we can bring out, okay, of the background, the another lower guided polariton that couldn't be observed before. So resonance here that we're starting to implement is very useful for having much better signal, higher signal to noise. But even more interestingly, what I would like to achieve is a form of strong coupling between the exciton and the phonon polariton, and achieve what we call this anti-crossing, and in a regime where these two quasi-particles would be strongly coupled. All right, let me conclude now with the slide I presented first. I presented first this scattering technique, SNUG, which is, very well known. It provides striking image and has been driven the progress in phonon polariton field for at least a decade. It has quite a few advantages, but it remains specialized, okay? What I presented on Raman backscattering is a complementary technique that could be used. Yes, it can only be diffraction limited, you cannot have a spatial resolution of 10 nanometer. And even at diffraction limited, you'll have 4K resolution. But if you don't need to do microscopy, you can improve the scale resolution considerably so that it's not a major obstacle. The selection rules are different between the two techniques, and it's always good to have choice of selection rules that can drive much more information for elucidating phonon polaritons. In both cases, spectral bandwidths are good, spectral resolution is good. The advantage of Raman spectroscopy is that it's readily accessible, easy to do. And also, Raman spectroscopy has a number of advantages, okay? There's no need for momentum matching strategies, right? So scattering doesn't require this nanostructure or this tip at the surface of the sample. Raman spectroscopy maps also these low energy infrared excitation where everything is very noisy, and maps them to the visible where detectors with single photon sensitivity exists. And by using resonant Raman spectroscopy, we could use this technique to couple different types of excitations inside the material. And I've also introduced a new material, gallium selenide, okay? And the confinement factor that I have reported were between 60 and 100. And that is exceeding some of the best values that have been reported to the two star hyperbolic polaritonic material that has been in the literature. The group velocity is not quite as good as for these other materials, but we hope that we could achieve the same thing by going to thinner and thinner layers, because as you make the thinner layers, you will flatten the dispersion curve and the group velocity will reduce. And the propagation length of the phonon polariton, which are at 25 micron in the boron nitride, we think we can match this. We have preliminary results that tells us that the propagation lengths are at least of the order of 10 micron as well. So we're introducing a material that is also quite interesting. So the details of what I presented here can be found in this publication. And that's it from me. Thank you for your attention. If you have questions, I'll be happy to answer. Yes.
Do you know why some material are better than other polaritons? Like what makes a material good?
What makes a material good? Well, I think it comes down to losses and lifetime, right? These are like the two characteristics of any excitation. So the lifetimes in boron nitride are in the tens of picosecond, if I remember well. And this is considered a long lifetime for non-polaritons, but in this lifetime, there can be significant propagation.
Yeah, but like, do you know of the structure, like the cell structure, like why?
I don't think it has to do with structure, mostly about losses. And what are losses is an excitation that is of interest. Here we would like a phonon polariton that travels over very long distances, for example, for achieving something coherent, for instance. But in the evolution of this excitation, there'll be coupling to other things, other excitations in the material. And basically, there's going to be a leak of the energy of this phonon polariton. So I think I cannot provide a better answer than saying that it comes down to losses. Losses can be take various forms, and it's a coupling of the polariton with other things, other polaritons, other phonons, and so on.
Thanks for the very nice presentation. I really like the complete story from beginning to the end. Great. So I have a couple questions. So the requirement of this double restaurant band is that you have to have a negative epsilon 1. Do you always benefit from going to lower temperatures and sort of eliminating the loss? Because as you increase the loss, of course, this goes up, right? And it can even cross 0.
Yeah, so most of the data I presented here was at room temperature.
Yeah.
But if we're interested in optimizing, propagation and so on, we can go to low temperature. We've done experiments at liquid nitrogen temperature again, for example. But I didn't get the relationship with the double Restrelan.
Yeah, it's just as you presented the dielectric function. Yeah. There was no loss. No imaginary part in the denominator. But as you add a gamma, so right, then as you turn this up, the electric function goes.
You mean in this region.
That's also
Yeah. So all of these parameters were required for simulating the Raman spectrum, and the lifetime. Lifetimes and these broadening factors needed to be introduced for getting something realistic, naturally. Yeah.
And the other question I had was, so gallium selenide is also an electro-optic crystal. So there's a possibility of generating light in the band where you would have a mode at photon-polariton mode. And Keith Nelson used to do these experiments years and years ago where he would just smack it with light, and then he would launch a photon-polariton mode in an electro-optic crystal. Yeah. I'm wondering if the same thing can be done in gallium selenide. Just smacking it with optical light and then launching a inflated photon-polariton.
I think so. I think there's a number of strategies to do that. I remember seeing some. Slide smacking. You're right. But wasn't there an interface, a special material that was deposited that were creating a suitable interface?
There's some scattering.
But definitely, I think this is. I presented some of these results to Keith Nielsen.
Yeah.
That did a lot of work in that, and that's what we discussed.
Yeah. Thanks.
Yeah.
Yeah, I was wondering, so you showed your electric field distribution in the Z direction, which is actually quite strong. And so that shows that there's actually quite a bit of variation in the intensity along the Z axis. So that also in principle means that the K value is not, the momentum space is not that well defined because you have quite a strong real space dependence. So what I'm wondering if you can also analyze Raman in terms of this real space variation, which is this approach by Haskell, which calculates Raman spectral of the real space. So I wonder if that approach might also give some interesting sort of insights on that structure of this spatial variation you have.
Yeah, but I would need to think a bit more about it. But my first intuition is to say that this is captured in the equation that I presented, because what we have in the equation where we calculate here, this particular term that takes into account this perpendicular, wave vector is the polaritonic field. So as this gets squeezed to lower in values, or depending on its periodicity, this term will have a significant effect. So I think it's already included in this treatment. And basically, this is our thickness. It controls the distribution of the field and the confinement patterns that are observed. And that might be very different scattering efficiency for different modes naturally. Are we talking about the same thing?
I think I'm not sure how much that other approach would actually shed different light on the
same. But that's interesting.
I'm curious because I think it's a very powerful way to think also about. Well, also unusual way to think about Raman scattering. But it's interesting.
All right.
All right, if there are no further questions, thank you for the fantastic talk and please join me in thanking.